This is about making RF designs work. This is a general overview about some of the pitfalls that there might be. And I've started with a Dilbert quote because I like this particular one. It's when Dilbert is being told to go and deploy a new wireless network. And he said, but that's going to take us months. And Dilbert's boss says, well, it's wireless. I mean, how hard could it be to not install wires? And that is the kind of perception, potentially, these days about, everybody's got wireless in their pocket, their smartphones. There's all sorts of different sorts of wireless technologies. It's everywhere. It's now settled down to be something which is just a commodity. Well, actually, there's still a lot of hard work in making a real product work sufficiently well. And I've just listed a few of the things that when you actually get into the detail of it, that you actually got to master the various aspects of the RF design process. So starting with a top-level block diagram, an architecture that actually delivers the goods, actually implements a solution to some sort of problem laid down by regulatory specs or whatever it might be. Break the architecture down into circuit level design below that. There are various different circuit blocks and circuit tricks involved in making a circuit actually do what it should do. Translating that from a schematic into a PCB layout. There are many pitfalls, and I've got some examples towards the end of this slot to explain how just doing PCB layout involves some RF skills as well. Integration of different disciplines between RF engineers and analog engineers, software, digital. Everybody is a specialist in their own particular area. Quite often the interfaces between those different disciplines can be an area of misunderstanding or disconnect. Getting the integration to work properly is an art in its own right. Some people don't know about derating and thermals. I happen to know a few examples of this, which probably better not say out loud, just in case it gets back. But certainly to make it a reliable product, to use all the components well below their rated limits, so maybe a factor of 0.5 on derating voltages and power dissipation and current consumption, this kind of thing. It can be a tedious thing going through an entire circuit, making sure that every part is not straining within an inch of its life. But that does make a big difference to the yield of a product out in the field. Well, we'll look a little bit later on at spurious signals and noise and the approvals process, but we have to make sure that we've designed a product that we expect to pass, rather than handing it over to a type approval lab and getting them to discover the problems that we hadn't foreseen. And then later on, the product has to get into the marketplace, it has to be manufactured in volume. There are issues with tweaking manufacturability processes to actually make a product be easy and cheap to manufacture and be effectively like shelling peas. So, lots of things to think about. So I'm going to explain my view on this using, firstly, a little story. This is my work of fiction. And then following up at the end of that with a few selected examples from my sort of back catalogue of war stories, and hopefully to maybe impart something useful that you might find relevant to your lives. So my little work of fiction is actually a story about a fictitious customer that wants a particular type of key fob for their car, which has got owner recognition in it. So Zumo Cars has come up with a product requirement, and they want to design it into their next prestige luxury car. So what they do is engage two different organisations, which will follow the success of the two competing organisations in this story. One of them called Classic Design Services, which are the good guys, and Shoestring Enterprises, which are not quite so thorough about things, and we will see the differences between those two. So, I'll introduce Shoestring Enterprises. They delegate their job to chief inventor named Chuck. And on the other side of the competition, if you like. Classic design services assign their task to a system architect. He has a different title. And that's how he looks. And both begin work right away on the project. So firstly, Chuck with Shoestring. He has a brilliant idea. I'm going to use a standard RF transmitter and an embedded micro from my previous project. And I think I can sense palm sensitivity to identify the owner. So he starts beavering away. He gets to work on his breadboard, and then with a couple of modules from Radio Shack and that kind of thing, he soon gets to the code hacking stage, which is brilliant. He has the project mapped out in his head. He hasn't got time to do a written down plan, obviously. It's only a short project anyway, so there's no point in that. And he's got well stuck into prototyping. Meanwhile, Randy talks to the customer. He plans his project and he discusses his project with the customer and the plan itself. He reckons it's going to take 6 months to go all the way from beginning to production. He works on establishing the protocol of the key code, and he gets some actual hardware in the car so that he can integrate and test ahead of time. And then he begins the task with a system architecture. Chuck's breadboard's really coming on. Actually, this particular breadboard is one from my lab, so. But I obviously made it look a bit more randomized than it really is in normal design work. He was so happy with his prototype that he invited his manager to come and have a look at it. Here it is. His manager was impressed. Some managers can be. And recommended him for a pay rise and set up the production in 4 weeks' time, because it's only little, isn't it? So the next thing to do is obviously to get a proper circuit board done. We're professional about this after all. So he quickly draws up the schematic by hand and then hands it over to the PCB bureau. If you've used PCB bureaus, they can take circuits, whatever ideas you have, and make you a circuit board from it. So it's an outsourced job. He just leaves it to the PCB bureau to do their thing, and actually can go off fishing for a week, which is fantastic. It comes back at the end, circuit board's done, all looks really good. So it looks like he's ahead. Question is Randy slipping behind? So he's finished his system design and he's working on an RF simulator to validate it. He then realizes that he needs some specialized baseband processing to handle the DSP algorithm. So he talks to one of his mates, who happens to be called Norm in this story. We haven't got his picture, but anyway, we know that he's going to work in a team on the DSP algorithm. And together they work out how the DSP and the RF is going to interface together and how the whole product will work. He's also asked for some clarification of manufacturing rules. And this question has led to the realization that it's going to be manufactured in the Far East using a different set of components than are locally available. So he's able to figure out some of the different package styles, and particularly for RF, if you find that you went from brand A of inductor to brand B of inductor, the parasitics are different, so he needs to actually factor that into his simulations as well. He's also concerned about tolerancing on a critical part of the circuit, and he spends a bit more time getting to the bottom of that. He's going to have to work hard now to complete the schematic entry on time. The PCB engineer expects to start tomorrow. It's always the case, isn't it? Now Chuck gets down to some testing. Well, powered up, that's always a good omen, isn't it? And there was no smoke. And the transmitter produces some RF. Now, because it's only a short project and he hasn't really got the proper kit, he decided just to test it with a power meter. And that was fair enough. And I suppose from the point of view of it being a short project, he can't actually justify the expense and the complexity of hiring any other kit in. Still, he had a scope and everything looks fine on there. All the voltages are good. And then he has a brainwave. puts all the stuff on a trolley, wheels it out into the car lot, and tests it on his own car. And success, his car unlocks. No more testing necessary. So Chuck's project is handed over to the production team, and they complain to begin with that many of the components are too closely spaced for the pick and place machines. How tiresome. So Chuck goes back to the PCB bureau and tells them to space it out more. So then he finds that there's a yield problem with the PCB, and that's because the holes that he specified are using too small a drill size, for example. And so they need to have bigger drills, bigger pad sizes, spaced out even further, go back again. They say they've never had this trouble before. But anyway, they'll fit in Chuck's rush job now as soon as they can. Meanwhile, Randy is still confident, and he's adding some more features to his owner recognition routine, and getting a little bit smug at this point of the story, I have to say as well. So production ran a few test boards down the line to prove things were going to work okay when Randy's board finally arrives. So Randy is still behind. His software is being coded and the PCB is being laid out. He seems to be forever working with a PCB guy to ensure that the critical parts of the layout are as they should be, messing about with different floor planning arrangements and critical tracks, maybe adding some shielding and screening areas, and making sure that there's good electrical isolation between the bits that need it. Power planes, ground planes, all that sort of stuff is being discussed between these two intelligent-looking guys. Chuck, however, starts to sense a bit of trouble. The initial tests on the production line are showing poor results. This is one of my favourite pictures, actually. Only 5 have worked so far. The rest of them seem to have gone into that wee recycling bin. Still, never mind. He takes his 5 working boards and heads off to the FCC approval lab for some testing. A nail-biting time. However, the FCC results are not quite the reading he was hoping for. There are a number of spurious emissions that are failing, and you need to do something about that. So that's what that Greek in there actually means, obviously. So Chuck finds it hard to hire a spectrum analyzer at such short notice, and his manager is starting to get a bit worried and annoyed about the extra unexpected costs. So he goes away and fiddles around with some little bits of tin plate screening. I'll worry about the manufacturing details later, he says. Finally, he puts the screened golden board back into its plastics and takes it back to the FCC, and at last it gets approved. So, Randy catches up. He's now testing his unit against a specification which he wrote for testing while the PCB was being made. He realised he would need some specialist RF equipment for this and booked it with a hire agency at the start of the project. I'm guessing that would be Intelligent RF, actually, since I'm stood here. Suddenly realised I haven't plugged what I should have done. Yeah. And Chuck should have thought of that as well. Let's come to that. So, once he's happy with the RF, he integrates the DSP stages and tests the two together. Then he spends a day at the FCC lab getting his certification. So, back with Chuck. He's nearly finished now, so he invites the client to a live demonstration. The client's management team assemble expectantly in that parking lot. Chuck presses his button and his car opens. However, so do half the other cars in the lot, and for some reason the car alarms are going off too. So So Randy finishes off his design. Now all he's got to do is to write up his final report and update his documentation. And as expected, 6 months have passed between starting the project and finishing it. Okay, it's a work of fiction, I have to admit, but that's what it says. So Chuck can't get the production yield to improve. Some of his units have poor range and the others have caused wideband interference. And 10 months into the project, Chuck's boss calls in a firm of consultants to review his design. I once was wondering who to actually put in that, but actually there's lots of consultants in here, so I can't pick one of you. So anyway, their report makes grim reading. They discovered that one of the key components used in Chuck's design can't be made to sufficient accuracy to guarantee all his units work, so a new architecture is needed. They found the reason for the wideband interference was that the VCO was far too close to the digital clock. The only solution is to start the board layout from scratch again. Chuck was beginning to regret taking that week off fishing while his board was being laid out. I suspect that he can have a little bit more fishing time in the near future at this rate. So, disillusioned at the lack of appreciation for 11 months of hard work, he hands in his notice and looks for a job somewhere else where his talents will be properly appreciated. So what did Chuck do wrong? So the first thing is he didn't do a project plan. He didn't analyse from the top level the processes that he was going to have to go through. He dived straight in. Same with the system design. Just wanted to get his soldering iron warmed up, and away he went with a solution that was already pre-prepared from a previous project. RF shielding, that's always an issue right at the end of a project, and planning for that at the beginning is a great idea too. If you put a little quart area of copper that's bare on the surface of your circuit board that encompasses where you might put a shielding can later, you can always fit it if you have to, or not fit it if you want to save some money. Deciding right at the end that you needed to add it means usually another board spin. So the layout details and the design rules, I mean, by leaving the floor planning and tracking details to a layout guy who is good at laying out but not necessarily good at RF, may be an issue. And this particular thing is one of my particular pet hates. I always find I have to sit next to the guy doing PCB layout, and between the pair of us we can satisfy both manufacturing rules, PCB layout design rules, and the possibility of getting the RF to work correctly as well. Tolerancing. Not often we think about tolerancing yield, production margins, that kind of thing. We need to have some standoff between the typical performance of our device and the extremities by which it's judged to pass. And test equipment. There's no getting away from having a proper bench worth of real equipment that's allowing you to test and see the real problems with your design. Having the right tools for the job is something that applies to this discipline just as much as all others. Finally, a bit of documentation doesn't go amiss. If you've kept everything in your head, then there's no way that a particular design can be spread amongst other people and enhanced if it's down to one person's particular ideas. So the second part of the pitch, just to take us all the way to lunch, is just to look at a few examples which are pulled from real life. I've got 3 just to look at here, which will show you a few things which you might find of interest in general about what has been necessary to make RF designs work in the past. So I've got an example of a case study of a module from a front end of a GPS system, a power amplifier that oscillated. Everybody knows that amplifiers oscillate unless they're supposed to oscillate. And then an idea about grounding and decoupling of an RF chip. I've actually taken a snapshot from an early stage of a circuit board layout, comparing it with a later stage to give you an idea of how circuit boards could be laid out in a way that's more likely to work first time. So the first of these, looking at a particular front-end module for GPS. The design brief for this particular project was that the GPS module had to be co-located with a cell phone. So that could be in some kind of Internet of Things device perhaps that has satellite tracking and connectivity at the same time, or in the old days a personal organizer with phone functionality and mapping built into it. So the key thing is that if you have an RF transmitter which is really close to a really sensitive GPS receiver, there is going to be some coupling. The transmitter is going to be shouting at the same time as the receiver is going to be straining to hear the small signals from the satellite. So the question is, how much coupling do you get between the two of them, and how significant is that? And this plot on the right-hand side here is actually showing two antennas which are co-located. The green curve is the return loss of a pentaband GSM 3G antenna, and then the red curve is actually the return loss of a GPS device. And the blue curve here is actually showing how the two couple together. So the issue is, if there is a lot of transmit signal at 800 or 900 megahertz, how much of that gets through to the GPS receiver? Admittedly, the GPS is expecting to pick up from a different frequency, but it can be completely saturated and overloaded by several watts of local transmit. And in particular, you can see that the coupling is more suspect if you look in the 1800 band, which is actually and 1700 band, quite close to 1575, which is where the GPS is intended to work. And also in the regular 3G bands a bit further up, there's also quite a lot of coupling possible. So in this particular development, we had to actually do some testing to find out just how much RF can a GPS system actually handle and still work at the same time. So this little graph here is actually showing what kind of transmit powers you might expect for a number of different radio standards, how much power is going to get through effectively through the losses of the two antennas which are coupling to each other. And then this is actually a set of measurements that were made as how much power level will it stand for that particular type of modulation and still do satellite tracking. So there's a lot of being quite unkind to a GPS module to find out at what point it fails to track satellites. And it turns out that it's not as small a level as you might have expected, but it turns out that you need to actually have some filtering to protect the front end of the satellite navigation chip in order that it does actually work sufficiently well with the full transmit levels. So this one's actually the earliest prototype that we did, and it's been evolved since then, so I've kind of avoided confidentiality by showing a design that's not actually in production now. But it's actually got the edge of the GPS antenna, and on the same circuit board we've got the GPS receiver chip. There's actually basically a serial digital output there. So all of this stuff basically takes RF in from the satellite and produces a location data stream coming out of it. So it kind of simplifies the design task of adding a GPS functionality to anything, really. These are 0201 passive components, so you can tell it's actually quite a tiny module altogether. So the key thing is this group of three parts over here. There's a bandpass filter, a low noise amplifier transistor, and another bandpass filter before it actually gets to the input of the GPS device. It turned out, after we did a number of different permutations, that simultaneously to get the noise figure that was needed and also the rejection that was needed, it actually took two filters with a low noise amplifier in between them to make it satisfy the overall requirements. This architecture is the one that was carried forward. We looked at the lower cost options of less filtering and less amplification, but this turned out to give a competitive advantage to this particular product. And this was done perhaps nearly 10 years ago now. And it turns out that more recently, just last year, I was working on a similar type of product where these things are available in a little ceramic module you can buy from Taiwan now, and you can't actually tell what's inside. But there are a number of different variants, some of them which actually have this front-end filtering and some of them which don't. There's yet another issue which I hadn't appreciated back then but have subsequently found, is that even if you have the GPS module switched off, there's a possibility that the local phone signal can actually be picked up by the front end of this receiver, cause rectification even in a switched off chip, and re-radiate it out the antenna some second harmonic. You can actually fail radiated spurious emissions just by placing a GPS device, even if it's not active, close to your GPRS modem. Which is avoided if you have this front end filter. It prevents the unwanted picked up signal from getting into the device and then being re-radiated. So it turns out that even today, when you can just buy a GPRS module and a GPS module and just stick them on a circuit board with no RF knowledge whatsoever, they can still fail. And it requires a little bit of system knowledge to understand what's making it fail too. My second example is of a power amplifier that was used in a VHF product for data communications. So there's actually a view of both sides of a circuit board here. It eventually goes into a sort of a metal clamshell which provides some screening between various different pockets. So this business of preparing the surface area with little compartments that can be used to mount a shielding arrangement. In this particular case, it was provisioned hoping it wasn't needed, and then it turned out to be absolutely needed. So it was quite good to have got the provision in the first place. So we're looking at both the receiver input and the transmitter output end of the product here. There's quite a large power transistor which is able to produce about 7 watts of RF in transmit mode. That gets coupled to a contact here onto which a VHF antenna is connected. There's also an auxiliary connector here, which is the car kit connector, and there's a RF connection over there. So a lot of passive parts in this region here are actually switching between the two possible antenna connections, internal or external. And it's also connecting between receive and transmit. So the transmitter output goes this direction, and actually the receiver input, the LNA, is over here, and there's some input filtering here on the other side of the board. So from antenna through to the receiver, or from transmitter out through to the antenna, is handled by some discrete switching. Now, you probably already read my punchline, the bullet point here. The issue was that this particular amplifier, when it was designed on its own by an RF engineer given that block of work, it was completely fine. Once it was integrated into the rest of the RF, so the receiver guy and the synthesizer guy and the power amplifier guy did all their integration together, and suddenly the amplifier, as soon as you switched it on, it was oscillating in a quite ugly way. And it turns out that there was a kind of feedback loop going on here, and as you can see from the bullet point, the radiation from this inductor here, which is part of the LNA filter, was actually magnetically coupled enough to this biasing inductor down here, which is on an earlier stage of the amplifier. There's a little RF transistor down there that this is biasing. So signal gets through that amplifier stage, through that one to the output one, and actually enough leaks through the isolation of the transmit-receive switch to feed a little bit of signal through the front-end filter of the receiver, completing a loop which hadn't been foreseen. I mean, took quite a bit of finding out, why is it oscillating? Looking at the stability of each individual stage, everything's fine. It's because there's a feedback path, a positive feedback path that wasn't anticipated. It's certainly not in the circuit diagram to give you any hints. It involves quite a bit of work to find out which are the things causing the remaining coupling. And it turned out that taking that inductor there and placing it 90 degrees round on the circuit board was enough to create enough isolation between those two parts. I think ideally we would have had more dividing lines between the receiver and the transmit. And it's unfortunate that there wasn't enough room to get another dividing wall in that gap there. Then we wouldn't have had this problem even in the first place. But that's the way history works out. So unexpected magnetic coupling between inductors is something which has haunted me at least half a dozen times in my career. So I'm now looking out for that as the first thing whenever I see multiple inductors on the circuit board. Are they orthogonal to each other or not? that's a good thing to think about when you're doing a circuit board review. My final example is this circuit board layout. And this is just an example from a random client, which I won't bother naming, by a PCB bureau that I also won't name. So the first cut of this particular circuit layout was done by the PCB layout guy without any input, because he worked remotely, and that was the way it turned out. So I want to draw your attention to some things on the left-hand side. Firstly, there's a power plane which is supplying, which is that little L-shaped section there, which is supplying the power to this particular chip. It's a small chip which does, again, Internet of Things type thing. It's a Zigbee, but at 2.4 gigahertz device. So it's a short-range RF product. And it has a power supply fed into a number of different places. So there is, in particular, RF for the transmit goes into these two pins here. RF for the receive goes into those two pins over there, and RF for the digital goes into those pins over there. And they are separate places on the circuit diagram, and they have been decoupled separately. But the way in which the decoupling has been placed on the circuit layout is suboptimum. So these orange coloured vias that I've colour coded here are where the power comes up from the plane, and you can see it more or less goes directly into the pins of the IC in those three cases. And then the decoupling is actually the other side of the via hole from the plane. So any interference that's come up from the plane can get straight to the chip without noticing the decoupling capacitor. And anything that comes out from the chip, which it does in the case of the transmit mode, can get down onto the power plane and then radiate to other pieces of circuitry without being adequately decoupled by the capacitors. So it turns out that you can get a much better performance simply by tracking things in a different order. So on the right-hand side is what's happened after I had a word sort of thing and changed the way in which it was done. So firstly, we've got a power track. There's just a track that runs to the three places needed rather than a whole plane, which means that a lot more of that particular layer is now ground plane, which is always good. And then it comes from the power supply through a decoupling capacitor, and then through, in this case, through a second one before actually going into the pins of the device. So by visiting the actual pad of the decoupling capacitor before heading to the device means that there's less series inductance in the way, and therefore the effectiveness of the capacitance is much greater. Same thing over here. You can see that it comes from the underneath power track through that decoupling capacitor and then eventually out of there into the two pins of the device. The only one that wasn't quite right is this one over here, where you've still got a little track up here. What should have happened is that little track should have bridged across from the pad of this decoupling capacitor to get into those two pins. But no, that's the snapshot I happen to have. It was eventually picked up. So it turns out that the layout on the right-hand side, actually from a radiation point of view, in fact for nearly every other point of view, we were very lucky because we'd paid attention to all this lot, and it didn't actually need any more relayouts at all. It was fine. First actual hardware spin that was received. And I'm pretty sure that this would have failed some regulatory emissions if it had been left that way. So there's a little bit of know-how, if you like, that can be put into circuit board layouts to make RF designs work. So at that point, final slide, you may have guessed that I advocate a methodical approach to this and not doing a sort of fast and loose hacking of circuit boards, no matter how fun it is to play with soldering irons and little components. As a stopping and thinking about it stage that's required first before we actually get into doing the actual circuit design. And the thought process about what could possibly go wrong needs to be thought through all the way from beginning to end. Maybe planning to decoupling, screening, ground planes, all that kind of thing, right from the beginning all the way through the product's development. And I finish with a couple of more quotes from Dilbert because I like those quotes. Again, these are from Dilbert's boss. I need you to finish it 6 weeks earlier for a trade show. Have you heard that before? I don't know, I certainly have. And the last one, I don't pay consultants for advice, I pay them to leave, and on that point, thank you very much.